Three, two, one, play. Alrighty, so we're jumping into the real stuff here. We got the phospholipid bilayer. Oh, the phospholipid bilayer is also known as the cell membrane. The subtle difference being that phospholipid gives us a serious amount of identity, but we're just going to start by recalling our idea of polarity. Got it? Polarity. So basically, the idea of polarity is we can think of some atoms, some molecules really, as these like perfectly balanced, happy things. And then we can think of other molecules as these really unbalanced, unhappy things. Sort of trying to describe it in shape, but it's usually more done with like color, right? Does that kind of make sense? Well, this guy is all one color, so he's all sort of balanced and happy. And then this guy is a mixture of two different intense poles. That makes sense? So this charge comes out to neutral everywhere, and whereas over here, let's say we have a negative charge. Over here, let's say we have a negative charge, and then over here we have a slightly more positive charge, or whatever it happens to be. So that's our basic concept of polarity. We have balances of charge across molecules, and this polarity really matters because it affects all sorts of chemical properties for all sorts of different molecules. So with the phospholipid membrane, we have this really cool situation where we basically have two different sides of the molecule with two different types of polarities. Because if you will also recall, double recall. Oh yeah, that's the good stuff. If you will also recall, is this alcohol? Sort of. Looks cool. You will also recall that not only do molecules have polarities, but these polarities are affect their relationship to different substances, such as water. So water favors polar molecules, right? So this means that on a basic level, if we're dealing with a very polar molecule, they'll be attracted to water. They will be hydrophilic. Hydrophilic. And hydrophilic, a nice simple one. Hydro is just water, and philos is just love. Yay. Hydrophilic. Water love. So the opposite of water love is, of course, as we all know, water hate. Hydrophobic. This is attained by nonpolar molecules. So hydrophilic water love. Hydrophobic. Water fear, technically speaking. And this means that a hydrophilic molecule will find itself attracted to a region that has water in it, and a hydrophobic molecule will find itself repulsed from a region that has water in it. In basic terms, if we dump a bunch of hydrophilic molecules inside, oh, I don't know, a glass of water, what do you think is going to happen? Well, there's tons of water in here, right? So it's going to dissolve super easily. You're going to have a really nice time. The hydrophilic molecule is going to be really happy. Right? If you dump a hydrophobic molecule in a glass of water, what are you going to have happen instead? Well, the thing's not going to want to go in there, right? So a good example of a hydrophobic molecule is oil. If I dump oil in water, what happens? It floats on the surface, right? It's like, no, I don't want to go in there. You could try and mix it together. You shake it up, it floats right back to the top, right? You know, this is just a basic consequence of the polarity of the molecules, of the actual molecular structure of these individual things. How does this relate to the phospholipid bilayer? In a very simple way. So the easiest and simplest way to conceive of a phospholipid bilayer is like this. Circle. Legs. Good stuff. The top over here, this circle bit, likes water. It's hydrophilic. This bottom bit, the legs bit, don't like water. It's hydrophobic. Envision for me dumping one of these guys in a glass of water, right? The hydrophilic bit is ultimately going to win. It's just going to like hang out at the top of the water, right? Sorry, hydrophilic bit. The hydrophobic bit's ultimately going to win. It's ultimately just going to hang out at the top of the water with its like hydrophobic end sticking out, right? And it's going to, because that's the bit that doesn't want to be in the water. There's one bit that wants to be in the water. There's one bit that doesn't. So the bit that doesn't want to be in the water sticks out, and the bit that does sticks in. It's that simple. What gets interesting is if you start adding more and more to more of these things in here, and if you start doing something crazy like start shaking up your glass of water that has all of your phospholipids in there. So this is a phospholipid. The name here is really cool and really simple. Again, phospholipid. Lipid is just a type of fat. Think of it like a fat. Phospho tells you what it is. It's a phosphate. Now, these phosphate groups, we've drawn phosphates a couple times. I'm not going to draw them again for you right now. Go watch the ATP video if you want to see me draw them. Simple molecules. It's in the chemistry section. Phospholipids phosphate is a very shockingly enough, hydrophobic or hydrolyphic. It's hydrophilic. It's a very hydrophilic molecule because it's very polar. It has these oxygens on its exterior, which are very vulnerable to being to having all sorts of funky stuff happen with them, and most prominently to not having hydrogens on them, and therefore having an electron imbalance. So lipids over here, the fats on the other hand, those are much more stable molecules. They're basically just hydrocarbons, right? And they're hydrophobic. So this basic setup means that if we add a whole bunch of these guys into a liquid, they start to form sheets, right? You get one section starting to form like this, and then another section starts to form like this, right? And if you leave this on the surface of the water, then you can have this attachment occur on the surface of the water, and you can have some interesting things occur. But if you start adding lots and lots of these things together, and you start shaking up the water, you get the spontaneous formation of membranes. And in fact, of basically functionally just straight up cell membranes. Now, one of the challenges is obviously you need a certain number of them before they start making nice circles, which is very true. And I do not have that number in this tiny space, so my guy looks a little funky. But I can cheat by adding in some big ones. Oh, look at me go. Perfect. Oh. Yeah, pretend I did that well. Excellent. So that's a bit better. And this is actually starting to look like a cell. So this is the basic dynamic by which the phospholipid membrane functions. And there's some really important fundamental takeaways I want you to have here, of which probably the simplest, gonna make my diagram pretty, of which probably the simplest really important takeaway here is that phospholipids and cell membranes are self-assembling. Right? They come together basically by themselves, and this material sort of drifts around cells and cell environments and all sorts of different structures. Sometimes it is fragmentary, sometimes it is in sheets, sometimes it is in bubble. All of these different sort of sections of cell membrane, of phospholipid bilayer, exist in all of these different crazy contexts. And it's really important to understand that that's just sort of a part of the cytoplasm and of the extracellular fluid that is really important in understanding sort of basic biological functions. You can sort of expect that stuff to be there, and in many of the examples we're going to look at, it's going to be there. So this is the basic sort of structure, but I hope you did go watch that video, but I am actually going to draw phosphates and a phospholipid for you, and we're going to break it down as well as I can, really, and continue taking it from there. So in order to do that, is there anything last I wanted to say? Spontaneous membrane development, polarity molecules, that's all good stuff. Let's get into the actual chemical structure of a phospholipid. And you'll remember now we're dealing really straight up. We've been dealing with micrometer scale a lot because we've been dealing with actual cells. But now we're going straight back down to nanometer scale. We're getting back into the actual molecules. We're dealing very, very small stuff indeed. So, what's the best way to do this? I think, let's draw this one first. This is an oxygen, phosphorus, oxygen. We got a negative on that to indicate ionic activity. Oxygen. I always draw my phosphates way too big. Then we have this sort of basic funky structure. This is why I needed a whole extra page for this, clearly. If you're at home doing this yourself, you can do this on like half a page. You don't need to use the entire notebook the entire time. But hey, if you're joining me in this massive diagram for no apparent reason, thank you so much. You're awesome. So, basic dynamics of a phospholipid. We have sort of this connecting structure here. Which we can see is organic. This is actually part of the head of the fatty acid itself. This is the carboxylic group of the fatty acid, or carboxylic groups, I believe. Carboxylics. Wow, that was beautiful. I nailed that. We're going to put yellow all over that so we know I did a great job. Carboxylics. Fantastic. So there's the carboxylics, and the carboxylics lead to nice, simple carbon chains, which we're just going to start denoting right like this. Each of this is just a C. So this one's already a C, and then there's a C here, 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 C here. This should be very familiar to everybody. It's saturated with a bunch of hydrogens. All is good. Now, if I draw another one over here, every now and then we don't have saturation. We in fact have another bond, and this messes up the bond angle and actually makes the bottom of the phospholipid different shapes. Phospholipids come in all sorts of different shapes and sizes, and with different sort of, so this R section up here, with different sort of attachments on the phosphate. So there's tons of variety. So you can have attachments on the phosphate, and then you can also have differing fats, which is kind of crazy. And there's two components to that. So that's the basic setup, chemically speaking, of your phospholipid. In terms of polarity, we obviously have this section over here, which is our phosphate. Our phosphate, we recall, is incredibly polar. Our polar things are things like water. That means that this guy likes water, so it's hydrophilic. This guy, on the other hand, is basically just a big chunk of fat. Fats and oils are very closely related to each other. If we toss fat in water, it wants to stay as far away as it can, so we know that this has to be hydrophobic. And there we go. So this is the basic chemical component of the cell, all the way down at the nanometer scale. Right? Tiny, 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 tiny stuff. If I remember properly, I'm going to double check this on the fly. I believe it's 10 to the 9. We're going to check. 2 billion. That doesn't tell me. Give me scientific notation. 10 to the 9. Whew, I got it. So that's 1 times 10 to the negative 9 meters. Right? Really cool, really tiny. So this guy iterated over and over and over. This guy iterated over and over and over, eventually gives us structures that look like this, and those structures themselves are the things that surround, are our cell membranes that surround things like our bacterium here, or our plant walls, or the inside of our plant walls here on our plant cells as well. Really cool stuff. Thank you so much for joining me. I hope it's all starting to come together. Have a great day. Tell everyone you know that they're cool. and that they should do cool things too.